We start our journey into polyphase representation taking a look at the analysis filter bank. So we start with writing our analysis filter with FIR filters of length capital L and downsampling operation in terms of our block index M and an in-block or phase index N with N between 0 and capital N minus 1. The original formulation for our subband signals for the convolution and downsampling with phase N0 was given by this equation here. Here we have our phase N0. Here is downsampling, and we have the sum N going from 0 to L minus 1, where L is the filter length of our FIR filter. In general, we assume that the filter length L is an integer multiple of N, and we can always zero pad it if necessary. We can now split this sum into an in-block processing with the phase index N that runs from 0 to N minus 1, and an out-of-block processing with the block index M prime, which runs from 0 to the end, by using an index substitution. In this way, the index M prime corresponds to our downsampled index. To obtain the same ordering for the signal X as we use for our block transform approach, with its index N going up, we substitute N by M prime times capital N plus N minus 1 minus N, and we choose the downsampling phase as N0 equals to N minus 1, and then we'll substitute from here, and we'll go to here. And then we have here a double sum, and we have this M prime now replaced N by this here, and we'll observe that this is still our filter bank formulation, but the interesting part here is that the inner sum again looks like our block transform formulation with blocks or vectors of size n and an impulse response along the column vector of length capital N. We can reformulate or simplify the inner sum as a vector multiplication when we rewrite the impulse response Hn as a vector which contains a sequence of blocks. So this is now the impulse response h of n as a vector. Okay. And we will use the vector of input blocks given here. Hence, we will get this equation now here, which is exactly the inner sum of 8. So here was equation 8, and now we have here. Hence, using these two vectors, we can replace the inner sum by this vector multiplication and rewrite or simplify equation 8 to this here. So now we have the inner part of the sum is now like our block transform. If we view our impulse response h of k as one column reversed of a transform matrix. So again, this is the transform view inside the filter bank view with longer filters, which is why we also have the outer sum, the out of block processing. That's a convolution. The remaining outer sum now looks like a convolution again, but now with a sequence of blocks instead of samples, and we have a vector convolution even here. Observe that our downsampling factor is now embedded in our block size. This has the advantage that we can now apply the z-transform to this equation to turn the convolution into a multiplication. First, we need to z-transform our vectors. So we will start with the signal vector x of m in the time domain, and we can compute the z-transform of each element of the vector as polyphase elements given here. So the z-transform of our signal vector x of m then becomes the polyphase vector. So we have here. Since we have n phases, we call this approach polyphase. We will use the same method for the vector of impulse responses. So we have here a vector of impulse responses, and then we will have the polyphase elements given by here. So this is our vector of impulse response, and then we have the polyphase elements, each one given by here. And the output of our case filter is still just a polynomial, not a vector or matrix, given here. The result of filtering and downsampling for the case filter in the Z domain is then the following simple multiplication of vectors. Observe here we rewrote the analysis filtering and subsequent downsampling by this multiplication of vectors in the Z domain. For an implementation, we can convert this equation back in the time domain, starting with rewriting the vector multiplication as a sum over the phase index n. So we will rewrite this vector multiplication as a sum over phase index n. The multiplications in the Z domain become a sum with simple convolutions in the time domain, which is here. This is the sum over the phases of the convolution of the blocks. With this equation, we can now implement the polyphase structure in the time domain. So here we have a visualization of the polyphase elements and the blocks. So given a signal x of n and a downsampling rate of n equals to 2, we get the following blocks and polyphase elements. So we have blocks and we have polyphase elements.